I'm Swati Raisam. I'll be facilitating this webinar. I'm a science associate at UCSF's program on reproductive health and the environment. All of you, for the purpose of this webinar, should be already muted and your video should already be off. We're going to ask that for lowering distraction, since there's a ton of people on, that you keep your videos off and that you stay muted. If you'd like to ask a question, please throw your questions into the chat. And we will collect them and hold them for a Q&A that'll happen after all of our presentations. So to just do a quick overview of our agenda today, Tracy Woodruff is going to present the project overview as well as the overview of our consensus manuscript. And then we're going to have lightning presentations from all of our wonderful lead authors. And then we'll roll into a Q&A for, fingers crossed, the last 20 to 30 minutes of this webinar before quickly going toward a close. So with that, Tracy, we'll start on your title slide.
All right. Well, first of all, I'd like to thank everyone for joining us and for your patience as we worked out a few technical issues. And welcome to our webinar. We're super excited to have everyone, and especially our lead authors here to present the results of a process that we've been engaged in over the last couple of years. Can you go to slide 5, please?
Yes.
And can you let me know, because I'm on the phone? Okay, thanks. All right. So the reason we're here today is that the systems in the United States for regulating and protecting us from harmful chemicals is not working. It's clear that EPA's methods for evaluating the hazards and risks of chemicals lags behind the science. Their methods have not changed significantly since the 1970s, and this results in people being exposed to toxic chemicals, particularly concerning for low-income and Black and Brown communities who suffer more greatly from these problems. Next slide.
Yep.
We have shown over and over that there's widespread exposure to toxic chemicals at levels that can increase the risk of numerous diseases, including neurodevelopmental outcomes, reproductive outcomes, and cancer. So this project is part of our goal to urgently identify the key steps that we need in order to create change that will improve health and health equity. Next slide. So the problem is getting worse. We are continuing to see unmitigated growth in the production of toxic chemicals. This data from EPA says there's about 9 trillion pounds of chemicals produced. We're seeing increases not only in chemical production, but the increase in plastic production and oil and gas, which also have ramifications for climate-related effects. Next slide. And we're seeing the impact in our health. People are increasingly suffering from chronic diseases, including, we're seeing increases in diabetes, neurological disorders, and asthma. And this is in part due to the fact that we are all exposed to many toxic chemicals before we are born. Slide 9. So our goal in this project, and what we're going to be talking about today, is to improve health and health equity by applying an updated framework that incorporates current scientific knowledge into policies and practices to account for the real world hazards and exposures from toxic chemicals. Next slide. So this is part of our science-based agenda for health protective chemical assessments and decisions. This was a effort, it was a collaboration among over 40 leading independent scientists and environmental health experts. And this has resulted in the 5 papers that were recently published in Environmental Health, which we'll be overviewing today: strategic and specific scientific-based recommendations to improve key aspects of chemical hazard and risk assessment to improve policy decisions to better protect health. Next slide. So we published a consensus statement that recommends a set of overall principles to address and reduce harmful chemical exposures. The first recommendation is that the financial burden of data generation for any given chemical or chemicals should be on the chemical producers that benefit from their production and use. Principle 2 is that lack of data does not equate to lack of hazard, exposure, or risk. It just means that we don't know what the exposures, risks, or hazards are. Principle number 3 is that populations at greater risk, including those that are more susceptible or more highly exposed, must be better identified and protected. Principle 4, hazard and risk assessment should not assume existence of a safe or no risk level of chemical exposure in the population. And principle 5, hazard and risk assessments must evaluate and account for financial conflicts of interest in the body of evidence. Go to the next slide. So in addition to the consensus statement, we have published 4 additional papers covering key areas of improvement that will lead to better decisions to protect health, which we'll be hearing briefly about today. The first is, actually, I think the order might be changed, but I'm just going to go in this order. The first is, one is by Dr. Vandenberg about improving exposure assessments in order to better account for real-world exposures. Dr. Warchowski will talk about population variability and approaches to improving methods to account for the full range of variability in the population. Dr. Nielsen and Hager-Bernays will talk about the paper on how to quantify non-cancer health outcomes to better reflect the real-world health consequences of exposures. So this will improve the basis of decision-making. And Dr. Maffini will talk about a class-based approach that will improve efficiency in evaluating groups of chemicals rather than one at a time. Next slide. All right, so now we're going to get to the very increasingly exciting part of this presentation, which we are really happy that all our lead authors of the 4 papers will be presenting quickly the overviews of their findings. And I want to also note that you can read more detail in our blogs. We also have accompanying infographics and, of course, the original papers that were published in Environmental Health. They're all available on our website. So now I'm going to turn it over to our authors. Thank you.
Yeah, thank you so much. Just to, again, reorient, because a couple of people joined in between Tracy's presentation. If you wouldn't mind staying on mute and putting your questions in the chat, we're going to capture them for later for the Q&A. But right now, I'm really excited to introduce Dr. Marcel Maffini. Marcel is an independent consultant based in Maryland, and for the last decade, she's been working on food and chemical safety issues and policy issues. Previously, she conducted research on cancer and endocrine disruption. And as Tracy said, she led our paper on classes. So Maricel?
Excellent. Thank you very much. Thank you, everybody, for joining us. This has been a very productive, fascinating project. And I am very pleased to be able to present some of the results on the science on chemical classes. And this I am presenting on behalf of the team. So next slide, please. So today we are going to talk about where this started. Tracy already gave a very nice introduction to where the project started. And then we will go through the process we follow to tackle the problem that we identified and how the type of recommendations that we are providing. Next slide, please. So it is very important that we basically propose and advance the science on chemical classes, because in our daily life, we are not really exposed to one chemical at a time. That is the way the chemicals are being assessed for risk and for hazard and the way they are managed now. And we know that these cumulative exposures are harming all of us. The assessments will be established. In the case of, if we are looking at classes of chemicals, there will be an exposure level for an entire group of substances rather than one accepted exposure level for each chemical. It would be for the entire class. There would be an increased efficiency in the way decisions are made, so better, more health protective decisions could be made in a faster way. And this is something that can be done, that others that have already done it, and this is one of the reasons we are we embarked in this particular project. Next, please. So this is the awesome group that I had the privilege to work with, and I want to thank every one of them for their participation. They are all brilliant. Next, please. So as I said briefly, the current system is looking at one chemical at a time when it comes to identifying their hazards, their risk, and their management. And it is really ineffective. And we are proposing here that we need a new approach to assess chemicals based on groups of our classes rather than continue with the status quo. And next, please. So this is the one chemical, one assessment. And I like to, my analogy to the process is that you imagine you have a sheep farm and your way to manage your flock is to assign one dog per sheep. So it is the way we are doing now with chemicals. We assign a large amount of resources to each individual chemical to assess their safety. And that with the thousands of chemicals that are already in commerce, and the increased demand for chemicals, this is a system that is unsustainable. Next, please. In addition, this is a system that allows for regrettable substitutions because some of the toxic chemicals that have been identified are usually replaced with others that look the same, that can have the same or similar functionality, but are usually less studied, so we create a new problem. Next, please. And more importantly, we are exposed to multiple chemicals at a time. We are not really exposed one chemical per day at a time. So the risks are always underestimated. So this is what we are proposing. It makes absolutely sense to group chemicals. And this grouping had many advantages, which includes reducing the exposures, because as I said at the beginning, we will be assigning an exposure level to a complete group rather than having each individual chemical having their own exposure levels. It allows for consideration of how the cumulative impact happened. Again, we are exposed to multiple things. We are looking at the impact of each chemical individually when we know that the exposure is cumulative and the impact in our health and environment is also cumulative. And as I said, there would be an increase in efficiencies, reducing cost and reducing time for decision making. Next, please. But not everybody is on board with this idea. We have heard already several concerns like, well, you are lumping everything together, the good with the bad, and what if we are putting good chemicals in a class that then will be highly regulated, or that the group is too small, that doesn't make sense, or the group is too big, that it becomes impossible to manage. But at the end of the day, this is all about concerns about increasing regulations to chemicals. So next, please. So we are creating a new framework. We are proposing this new idea, and we actually review a number of laws, regulations, guidance documents, both in the US at the federal level and state level, and also in the EU. We collected the most amount of information that you can imagine, and we sort through it to identify whether there are already methods that are being used for grouping chemicals, what are their legal requirements, and what can we do with this information. So next, please. So what we found is that there is not a single grouping method. Of course, that's pretty obvious, but we identified 19 different sources that contain grouping methods. And the most common group was chemicals that are similar in structure, that they look alike. That assumption is based on the fact that then if a chemical looks alike, it will have similar functionality, they will have similar toxicity, they will have similar fate in the human body and in the environment. So we also identified that there are different regulatory approaches for grouping. In some cases, the type of grouping is included in the letter of the law or is already included in the regulations. And that depends on what the legal mandates are for the different agencies. And we also identified new and emerging scientific models around grouping, like systems like the key characteristics or adverse outcome pathways, that they would be based mostly not necessarily on how similar the chemical structure is, by the similarities or the shared biological mechanisms. Next, please. So as I said, there are different methods for grouping. Very quickly here, just reviewing similar chemical structure, similar physical and chemical characteristics, whether chemicals are persistent in the environment, if they bioaccumulate in the body or through the supply chain, if they are toxic under the specific sections of the law, if they cause toxicities to the same organs, or they cause the same similar health problems, and also if they have common functions, for instance, for pesticide uses or flame retardants and the like. Next, please. So we also identified one success story, that is the regulation of a class of chemicals in the US called orthophthalates. That was a success story. This was the Consumer Product Safety Commission was mandated to regulate orthophthalates for children's toys and children's articles. They were grouped based on children's health concern that these orthophthalates are affecting male reproductive system development, and the management of this chemical was through effectively a ban. They reduced the amount of these orthophthalates allowed in products to a very, very small level, so it's effectively a ban. However, one of the concerns is that the same agency that regulated and banned these phthalates continue to allow them in other consumer products. The Environmental Protection Agency now is under consideration of these phthalates. They may also consider them as a group, but not necessarily. It's not that is there's a process ongoing, and the Food and Drug Administration allowed many of them, 6 of them specifically, to be used in food and be in the diet without necessarily having any limits. So we see here a disconnect between something that has been successfully done, but is not applied consistently within the same agency and with other agencies that are regulating the same chemicals. Next one, please. So we propose that any chemical can be grouped into, can be grouped. It's a process that we call decision tree. It is chemical agnostic, but it's based on 2 equally important principles. That is the context of the decision that is going to be made and the scientific considerations that are used to develop the group. And this is this decision tree, we hope, will help develop the best possible class to achieve a health protective regulatory outcome and avoid regrettable substitutions. Next, please. So among this, the decision context, transparency is very important. And the other thing that we want to point out is that this is not just for regulatory agencies. Any entity that is interested in deciding on chemicals can use the decision-making to select the best possible group to meet their goals. It could be manufacturing decisions based on groups of chemicals that the companies don't want to use, or making purchasing decisions based on groups of chemicals that are preferred over others, or government agencies using these decisions, this grouping for prioritization purposes. So next one, please. When it comes to the scientific considerations, we identify 3 buckets. It could be based on physical chemical properties. Let's say a company decided that they manufacture carpets, for instance, and they decided that they don't want any chemical that will remain persistent in the environment and it will be bioaccumulative. So that would be their scientific consideration for the class of chemical that they don't want to put in their products. And then we have toxicity profiles like carcinogenesis or developmental toxicity, and also the occurrence. The uses, the functionalities could be used as a way to group chemicals, or if there is a type of co-exposure. Next one, please. So how do we envision applying this decision tree? This would bring flexibility, and this will bring also interaction between agencies. For instance, in this example that we have in the publications, we identified, we proposed, for instance, the first question would be, what is the decision context? Is this a new regulation? Or is an old regulation? If it is an established regulation, is the class defined in the regulation, or is it not? If it is, follow the prescribed method. If it is not already described in the regulation, we propose to look at whether or not there is a precedent at the agency for grouping, or at other agencies if they already have a grouping for those type of chemicals. So this is our understanding of a more progressive and more protective system would look like. Next one, please. So our recommendations again is that the decision makers group chemicals in classes or categories whenever possible. We identified laws that are prescribing classes. We identify laws that are broad in the discretion of the agencies to identify the different classes. But we are urging everybody to use groups as much as possible. And applying this decision tree, again, provides flexibility with the opportunity to systematically incorporate chemical classes into the decision-making process. Next one, please. And this is just a brief summary that the decision tree has several advantages and advances the use of chemical classes because it offers flexibility. There are multiple variations in approaches. It works with a tested or a brand new approach. It is grounded again on the decision context and the science. The science evolves, therefore the flexibility is important, and also stimulates coordination because questions about existing grouping methods that increases collaboration between agencies and also within the agencies. So I think I have one more slide, and that is to thank you all.
Awesome. Thank you so much, Maricel. Just as a reminder, I've been seeing stuff in the chat. So we're going to be holding our questions until the end. And up next, we have Dr. Julia Warshawski from Northeastern University. So Julia is an assistant professor at Northeastern. Her research focuses on reproductive and developmental health impacts of endocrine disruptors commonly found in consumer and personal care products, and identifying opportunities to reduce exposure and improve health among vulnerable populations. She led our paper on variability and vulnerability. So Julia, whenever you're ready to go, I'm on your title slide.
All right, sounds good. So I'm on the phone. Can you hear me?
Yes.
Okay, great. So I'm going to be following along on my slides on the computer, but I'll just be saying next slide. So do forgive us if we run into a few issues that way, but we'll do our best here. So as Swati said, I'm at Northeastern University in Boston, Massachusetts, and I'm going to be talking today about our paper on advancing the way that we capture human variability in chemical risk assessment to account for susceptible subgroups in the human population. So next slide. So for today's talk, my objectives are to share with you the one-sentence problem statement, describe who was in the room to try to address that problem, demystify the current EPA approach for how we currently account for human variability and susceptibility in chemical risk assessment, and then talk through some existing and emerging data which suggests the current approach is outdated, and then compare the current approach, EPA's current approach, to other approaches by other regulators.
And then I'll conclude by highlighting some recommendations going forward. Next slide. So the problem that I'm addressing today is that current U.S. chemical risk assessment practices do not account for the full range of human variability in response to environmental chemical exposures in a way that adequately protects the entire human population, which includes sensitive subgroups. So in other words, and this is an animated slide, oh, there we go. In other words, when the US EPA evaluates chemical risks, it assumes that we're all pretty darn similar, or more specifically, that some of us might be about 10 times more sensitive than others. But, you know, we wanted to understand if that approach was actually appropriate. Are we that similar when it comes to the variation in the way that we respond to chemical exposures? Next slide. Oh. So the problem, or so, hold on, sorry, the team. We're on the team slide, right? So
Yep.
We assembled an interdisciplinary collaborative team to tackle this problem, including representatives from both the scientific and NGO and policy advocacy communities. So some of these folks have also been in the field for many years, some with over 30 years of experience in this group, and then some also newer faces as well. Next slide. Our current approach. So the current typical approach of the US EPA right now is for non-cancer risk assessment is to use what's called a 10x adjustment factor, which is basically the equivalent of dividing a value that we think is safe for the average healthy human by 10 to account for some humans being 10 times more sensitive than the average healthy human. And if the original value came from an animal study, which it often does, we first divide it by 10 to extrapolate from animals to humans. And that assumes humans are 10 times more sensitive than animals. So looking at the bottom of this slide, you can see that the original value from an animal study is divided by the blue 10 to first account for animal to human extrapolation. And then you divide by the orange 10 to account for that assumption that the most sensitive humans are 10 times more sensitive than average healthy humans. And that gives you the magic number that is supposed to protect everyone, or at least almost everyone. And the reason why I noted this is non-cancer is because we're just going to cover non-cancer in this presentation, and it was our main focus of the paper, but I did want to make a note that for cancer, not even the bare minimum to account for human variability is really done for cancer. All right, next slide. So these basic tenfold adjustment factors for non-cancer risk assessment is that goes back to 1954, when Lehman and Fitzhugh at the FDA identified a maximum dose at which no effects were observed in animal experiments. And then they divided that by 100 to get what was deemed an acceptable margin of safety with regard to food additives and human health. So our current practice hasn't changed since the 1950s, which is almost 70 years. Next slide. But we asked the question of whether it is really safe to assume that sensitive humans are only 10 times more sensitive than healthy average humans. So for example, what about sensitive life stages of development, such as in utero development or development during early childhood? Or what about populations that are also burdened by other co-exposures? And that can include chemical and non-chemical stressors like poverty, racism, low socioeconomic status, etc. Next slide. So, and the truth is that there are many sources of human variability and susceptibility in our population. And that includes intrinsic factors or internal biological susceptibility factors like age, life stage of development, like genetic makeup, like pre-existing conditions or underlying physiological status. And it also includes extrinsic or external susceptibility factors like poverty, like psychosocial stress, food insecurity, and other co-exposures, say from air pollution or additional occupational exposures. Next slide. So these factors can all increase our risk for disease and or our risk for an adverse outcome. And you can think of it like this, that these internal and external susceptibility factors can shift the population or sensitive subgroups closer towards clinically defined physiological thresholds of disease status. So the example I have used before is that pregnancy is a critical period for maternal health that is accompanied by extreme changes to maternal physiology, which occur to accommodate the developing and the growing fetus. So things like insulin resistance naturally during pregnancy increase for the fetus to be able to develop and grow. And that increased insulin resistance, the intrinsic factor of being pregnant, can put more pregnant people over the clinically defined threshold of disease status with respect to diabetes during pregnancy. So instead of 1 out of 10 pregnant people above the disease threshold line in red, the top row, we might now have 3 out of 10 pregnant people above the disease threshold line in the second row, just due to pregnancy. Then on top of that, if you add other external risk factors like exposure to metabolic disrupting chemicals or other co-exposures that promote insulin resistance, it can shift even more pregnant people above that line, and now we might have 5 out of 10 with the disease in red on the bottom row. So the bottom line of all this is that these internal and external susceptibility factors can either separately or together enhance our risk for disease. Next slide. And there's lots of newer data suggesting that the range of our responses to chemical exposures, the difference between sensitive and average humans, is much greater than 10. So for one, the National Academy of Sciences has already presented several examples in their 2009 Science and Decisions report, showing how genetic susceptibility, pre-existing disease, and interacting chemical exposures can increase our sensitivity by more than tenfold compared to control. So for example, some of the most classic examples are that smokers have been shown to be 20 times more sensitive to arsenic-induced lung cancer than non-smokers. Women who smoke and have low iodide levels are up to 100 times more sensitive to perchlorate-induced thyroid hormone disruption than their control counterparts. And we also have data from the scientific literature since this report showing similar trends, such as greater sensitivity to chemical exposures among young infants and children, among the elderly, etc. So for example, one recent study by Josh Robinson's lab at UCSF published in 2020 showed that up to 12,000 times lower expression of enzymes that are needed to metabolize environmental chemicals in second trimester fetal liver samples compared to adult livers. So that just is more data supporting this notion that we are more different than the 10x factor accounts for. And then based on other differences in age and metabolism with respect to air pollutants specifically, the California EPA, the Office of Environmental Health Hazard Assessment, OEHA, has actually increased its default adjustment factor from 10 to 30 to account for more sensitivity differences between young children and infants compared to adults. And they also more recently even set an adjustment factor for benzene specifically at 60-fold to account for not just differences in sensitivity across age groups, but also to account for genetic susceptibility, genetic polymorphism. And then finally, I wanted to make the point that the IPCS, the International Program on Chemical Safety, commissioned by the World Health Organization in 2014, a report that demonstrated up to 42-fold variability, a 42-fold range of variability in response to chemical exposures when they evaluated data probabilistically. And I'm not going to go into the complexity around probabilistic data. That's actually going to be covered a little bit in a later presentation as well. But the important point I want to make is that this was based on primarily on data from healthy adults, this variability of 42-fold. And, you know, this is just further indicating that a 10x adjustment factor just doesn't cut it. Next slide. So ultimately, based on all of this information, we recommended, we recommend to regulators that we think it makes sense as a starting point to increase the default human variability factor from 10 to 42-fold, unless there's robust data to the contrary, to reflect the data that I just talked about from the WHO, which essentially highlighted biological differences in susceptibility between adults that were greater than 10-fold to 42-fold, up to 42-fold. And then another key recommendation is to create a separate age-related adjustment factor for sensitive life stages of development, which is based on the OWIHA data, where they increased their default to 30 for criteria air pollutants, and then even up to 60 for benzene specifically. And another recommendation I really want to highlight is that to create a separate default external variability factor in addition to the 42x and age-related factors I just mentioned that would account for multiple chemical and non-chemical stressors. So this factor could account for human variability in susceptible subgroups. For example, if there are interactive effects associated with low birth weight that are much stronger in Black women, an additional factor should be applied if low birth weight is an effect of the chemical that's being assessed. And then ultimately, we need to use updated science, updated methods that include, and again, I'm not going into this here in detail, but that include probabilistic methods and that also integrate data from multiple different data streams. So multiple heterogeneous data sources like human studies, human epidemiologic studies, animal studies, in vitro studies, etc., which would allow us to better capture the full range of variability and the full range of complexity in the human population with regard to how we respond to chemical exposures. And we feel we've demonstrated that we have the data and the tools to do this better, so why not? And I will end there, next slide, just by saying thank you and referring folks to our paper, to the blog on that translates these findings, and to the infographics that may be helpful in communicating this more broadly. Thank you.
Amazing. Thank you so much, Julia. We're going to move on to our next presentation by Graylin Nielsen and Wendy Heiger-Bernays. So just to briefly introduce the two of them, Wendy Heiger-Bernays is a professor at Boston University. Her research focuses on the toxicology and health risks of PFAS chemicals and PCBs, and the impact of industrial chemicals, consumer products, and pharmaceuticals in water and waste streams on people's health. She co-led our paper on probabilistic methods with Graylin Nielsen, who you're about to hear a ton from. Graylin's a PhD candidate at BU as well, and her research focuses on using human relevant systems to probe the nuclear receptor mediated effects of PFAS and trying to figure out ways to improve risk assessment practices to produce evidence-based reference values that truly reflect population variability and vulnerability, which you'll hear about a little bit now. So Graylin and Wendy, are you ready?
Ready. Thank you so much, Swati.
Awesome.
Yeah, thank you for introducing me. My name is Graylin Nielsen, and I'm presenting on behalf of the team that looked critically at the process here in the US of evaluating health risks from exposure to environmental chemicals that cause non-cancer health effects. So Dr. Warshawski's paper focused really closely on evaluating the current process for evaluating non-cancer health risks and whether it's adequately protective of variability in the human population. And our analysis focuses on whether the current methods are leveraging the best available science to set acceptable exposure levels that are truly protective of public health. We can go on to the next slide. So I'll be talking about EPA's current approach to evaluating non-cancer health risk from environmental chemicals, and I will introduce our research team, describe the results of our research project, and the key recommendations that follow from this work. So here is the team. The work came about as a multi-institution collaboration with experts in multiple different roles with specialties in different disciplines. And the issue that we're really focusing on the next slide is that US EPA is required under the Toxic Substances Control Act to use the best available science to evaluate the impact of toxic chemicals and make decisions that protect human health and the environment. However, EPA currently does not quantify health risks from non-cancer health effects of toxic chemicals, which is inconsistent with multiple published works describing and demonstrating methods to do this better. And we can go on to the next slide. So health risks from environmental chemical exposures are assessed differently for cancer versus non-cancer health effects. And this difference has several important implications that I'll introduce shortly. But first, for the non-cancer health effects, the risk assessment process assumes that there's a safe level of exposure to environmental chemicals, which basically means that the chemical exposure does not increase risk of disease as a result of exposure. Regulatory agencies determine that safe level based on animal toxicity studies or human epidemiological studies. And exposure above that safe level is assumed to increase risk of illness, while exposures below that safe level are not expected to increase risk of illness. However, this method does not quantify or describe the risk of developing disease at any chemical exposure level. On the other hand, for cancer risk assessments assume that any exposure to a carcinogen increases risk of developing cancer. Regulatory agencies define the relationship between increasing exposure to the carcinogen and risk of cancer. And the regulatory values are selected based on this relationship to be exposure levels that cause only a minimally increased risk of cancer. And typically, an acceptable risk of cancer is defined as an additional 1 in 1 million excess cancer cases due to the chemical exposure. Having a quantified relationship between the chemical exposure and risk of cancer makes it possible to perform cost-benefit analyses and place a dollar value on the healthcare and related savings associated with exposure or minimizing exposure to chemicals in the environment. So we can use the example of perchloroethylene on the next slide to understand these differences in risk assessment processes. So PCE, sorry, I'm turning my video off here because my phone is telling me it's low on battery. So again, we can use the example of perchloroethylene to understand the differences in risk assessment. Perchloroethylene, or PCE, is a solvent that is used in the dry cleaning industry and also in the metal degreasing industry, among other uses. And it's volatile, meaning it readily vaporizes. And as a result, an important route of exposure for human populations is through inhalation, though PCE can also be mobile in water and soil and can be ingested through those exposure media. Studies in humans and animals show that PCE exposure increases risk of multiple adverse health effects, including both different types of cancer and multiple non-cancer health effects. So the non-cancer health effects vary in severity. Acute exposure to PCE can cause dizziness and headaches that may resolve when the exposure ends, while long-term exposure to PCE can impact brain function, with studies of dry cleaning workers and communities exposed to PCE showing an association between long-term PCE exposure and decreased performance on multiple neurocognitive tests that are measuring different types of brain functions, such as visual memory. And additionally, studies in communities exposed to PCE in drinking water show increased risk of miscarriage and stillbirth. And these are just a few of the health effects associated with PCE exposure in the epidemiological literature. Exposure to PCE is also associated with developing multiple different types of cancer. Studies in human populations exposed to PCE show increased risk of bladder cancer, and animal toxicity studies show that PCE exposure through inhalation or ingestion increase the incidence of liver cancer. And we can move on to the next slide. Regulatory agencies have set allowable exposures for both non-cancer and based on both the cancer and non-cancer health effects. And the regulatory value for non-cancer health effects is based on neurocognitive impairment. For the neurocognitive impairment, the regulatory value or acceptable exposure level can be interpreted as follows. It's the estimated lifetime PCE exposure expected to be without appreciable risk of neurocognitive effects is this particular concentration. And so in other words, that's the concentration of PCE in air that is not expected to increase risk of neurocognitive effects. For cancer, the regulatory value is based on increased incidence of liver tumors in animal studies. And that regulatory value can be interpreted as follows, which is the estimated increased risk of liver cancer from lifetime exposure to PCE is 2.6 times 10 to the minus 7 liver cases per microgram per meter cubed of exposure. So with that very specific information, the risk of cancer due to PCE exposure can be calculated for any exposure level, including comparing a higher exposure level to a lower exposure level, which can inform cost-benefit analyses and help understand the benefits of reducing environmental chemical exposure. Next slide, please. So there are several important limitations with how current non-cancer risk assessments are done that could be improved upon if non-cancer risk assessments looked more similar to cancer risk assessments. And Swati, I'm sorry, this slide has several animations. Yeah. So first, non-cancer risk assessments do not quantify the likelihood of developing the non-cancer health effect at different exposures. And it also does not describe how many people are expected to develop that health effect. There's also no consideration of the severity of the non-cancer health effects in terms of the degree of damage to a particular organ or system. So going back to our example of perchloroethylene, very high exposure levels can cause physical changes known as solvent encephalopathy versus a less severe health endpoint like reduced visual memory functions. And finally, non-cancer health effects do not address uncertainty or variability in the regulatory values adequately, as you heard a little bit from Dr. Warshawski. And then looking at these uncertainties, we actually do have data and methods to do this better. And given EPA's mandate of using the best available science, the goals of our research paper are really to look at the methods that we have and how we can implement them to improve the risk assessment process. So on the next slide, I've just laid out our research goals again. There were two primary goals with this project. The first was to review the literature to identify research methods that address the limitations in current non-cancer risk assessments. And secondly, we then applied these methods to a case study with the chemical that I introduced, perchloroethylene. And I'll go through both of the findings from these different aspects. So the first important finding from our research project is that there are multiple methods available that have been described to quantify the relationship between chemical exposure and non-cancer health effects. These methods can be applied to perform non-cancer health risk assessments that produce similar results to cancer risk assessment. And collectively, these methods are known as probabilistic risk assessments. So then we looked at the different methods that were available and chose to use a method recommended by the World Health Organization, which allows us to disentangle uncertainty and variability and allows risk managers to set reference values that specify the severity of health effect and the incidence of the health effect. We applied this quantitative method to the example with PCE because PCE was listed as a high priority chemical for evaluation by the U.S. Environmental Protection Agency under the Toxic Substances Control Act. And our analysis relies on a critical study underlying EPA's current assessment for PCE exposure, which was by Echeverria et al. And it examines PCE exposure and neurobehavioral outcomes in both dry cleaning workers and clinical patients with solvent encephalopathy. And the non-cancer health effect in this analysis that we used, just to go back to the last slide real quick, is the effects of PCE on visual memory. And visual memory is an extremely important brain function that describes the ability to learn and remember information that we see. So visual memory is a critical component of learning to read and write. For example, because a reader is forced to recall images of words, and writers also have to recall what each letter looks like when they're writing. So our analysis found that 1 in 1,000 people are predicted to have reduced visual memory function with exposure to PCE at the level that EPA currently considers an acceptable exposure level. So this graph on the bottom is showing the results of our analysis, which defines the relationship between the concentration of PCE exposure and the incidence or occurrence of the visual memory impairment at the population level. So you can see that as PCE exposure increases down on the horizontal x-axis, the occurrence of visual memory impairment on the y or vertical axis also increases. And the vertical lines here in this figure are just noting the concentrations at which 1 in 100 people and 1 in 1,000 people would be expected to have visual memory impairments from PCE exposure. So as I mentioned, our results are showing that exposure to PCE at the current regulatory value is expected to result in 1 in 1,000 people having reduced visual memory function. And we wanted to compare the risk for this non-cancer health effect to the risk of cancer at the same exposure level. So for key finding number 3, first off, EPA typically assumes that regulating chemicals based on cancer risk, when there's a chemical that causes both cancer and non-cancer health effects, EPA assumes that a regulation based on cancer risk will be protective for non-cancer health effects. However, we found that risks for the non-cancer health effect here are much greater than cancer risk at the same exposure level. So our analysis shows that the risk of visual memory impairment at the regulatory value is about 100 times greater than the risk of cancer at the same exposure level. And that opens a conversation for a risk manager to then compare the severity of those two health effects and make decisions based on that comparison. So for take-home messages on the next slide, this project is an important contribution to improving risk assessments for non-cancer health effects. And our analysis is showing that updated risk assessment methods that quantify the relationship between chemical exposures and non-cancer health risk can help set clearly defined acceptable exposure levels for environmental chemicals. Based on our research, we recommend that regulatory agencies should incorporate probabilistic risk assessment methods into their current practices, because these methods can really provide greater context to existing reference values. And they do so by describing the probability of effect across a range of exposure levels and have more consideration of the population in question. We also think these methods can relate the effects of chemical exposures to clinical disease risk so that resulting risk assessments can better inform decision makers and cost-benefit analyses. And moreover, these methods also do a better job of reflecting the underlying biology and uncertainties associated with population risks. So incorporating probabilistic risk assessment methods will ensure that regulatory values are transparently defining health risk when we're setting acceptable exposure levels based on non-cancer health risk. And with that, I think I will turn it over to our next presentation.
Yeah, thank you so much, Graylin. That was great. And also thank you everybody for hanging on. I wanted to note that the original webinar time is technically until 11:30 Pacific, but because we got a late start, we're going to go a little bit late. For folks who might need to hop off because they have alternative or have other meetings or other commitments, we are recording this and we do plan to share it out. So please, let us know. But with that, I am very excited to introduce our next speaker and our last presentation, Dr. Laura Vandenberg. Laura Vandenberg is a professor and dean at the University of Massachusetts Amherst. Her research focuses on the impact of early life exposures to chemicals and chemical mixtures on disease outcomes over the life course, as well as the impact of low-dose exposures on health outcomes. And she led our paper on exposure assessment. So Laura, are you ready?
I'm good. Can you hear me?
Yes, I can.
Great. Thank you. Thank you so much, Swati. And thank you all for sticking with us this afternoon. And of course, I'm presenting on behalf of a much larger group that I'll also introduce to you in just one second. So let's move to slide 2. So similar to what you've already heard from the other speakers, I'm going to give you a sense of why did we choose to focus on exposures related to environmental chemicals, what we did to tackle the problem, the team that was involved, our specific approach, and then, of course, the recommendations we'd like to make. So let's move on to slide 3. I think you've heard a couple other metaphors here today, and I really like this metaphor about how when we're trying to protect the public's health from environmental agents, including chemicals and contaminants, there's many different parts of this chain. So when agencies want to evaluate a chemical, they want to know what harm does it cause. They want to know what exposures lead to that harm. They want to know how much is released into the environment or enters the bodies of people. And then they want to know to what degree those things are related. So each of those steps is a part of a chain, and a weakness in even a single part of that chain can break the entire thing. So let's move on to slide 4. This is really going to bring us to our idea of focusing on exposure assessment. And after our paper was published, I don't know if it was a week ago or a little bit longer now, we did get some emails from folks who said, why are you focused on exposure assessment? There's lots of other problems. And we agree, there are lots of other problems, but it's really important that we understand how people are exposed to chemicals, how wildlife are exposed to chemicals, so that we can use the best available science to understand and quantify those exposures. So let's move on to the next slide. So the problem that we really wanted to focus on was that there are a lot of sources of uncertainty in exposure assessments. And when those uncertainties contribute to underestimates of exposure, they make the validity of risk assessments in question, and ultimately they put the public at risk. So our team decided that we wanted to identify big and important problems in exposure assessments, and then use those case studies to be able to make recommendations for how better policy or regulation could be used to address those problems. And in particular, we wanted to focus on where the best available science could be used immediately. So not just a call for more research or more information. Let's go to the next slide. So this is our fantastic team. And like all the other teams that you've heard about today, this one really brings together people from a lot of different backgrounds and approaches and ways of thinking about exposure assessments, the policy and use of those exposure assessments as they relate to animal studies, epidemiology studies, and community engaged projects. So at the next slide, just as a brief overview, one of the things that we wanted to do was to understand how exposure assessments are actually used in each of those different areas. We identified several case studies, as I mentioned, that could illustrate how flawed exposure assessments are occurring, but not just that they're occurring, how they put the public at risk. And then based on those case studies, we made some recommendations. So let's move on to slide 8. First of all, exposure assessments use very well articulated, very well described methods of being able to determine what people are exposed to. And remember, when we're talking about exposure assessments, sometimes we're trying to measure how much of a chemical has been released by a pollution source, or we might want to calculate how much is found in a consumer product and then estimate how much people are exposed to by knowing how much of that product is consumed, or we might want to actually measure what's found in the bodies of people by looking at blood or urine or hair or some other bodily fluid. So exposure assessments use one of these different approaches as a way to try to understand what is actually entering the body. And they might do that at the boundary of the body and the environment, or they can do that by placing a monitoring device near the individual, or sometimes again by collecting biological samples from people so that we can use what's found in urine or blood or some other biological matrix to try to understand what's going on internally to the body. So next slide, please. So an exposure assessment is a really important part of the risk assessment process, which I've already hinted at when I was talking about the different links in that chain. We want to know what are the hazards of a chemical. We want to know at what levels of exposure would we expect to see those hazardous outcomes. But we also really need, and it's a fundamental part of risk assessment, we need to know how much of that chemical pollutant are people exposed to. And usually that's bounded by a specific period of time or a specific subpopulation that we might be interested in. Next slide, please. We also have to remember that exposure assessments are really critical tools to be used by communities and by people who are out in the world studying the impact of exposures on communities. So on the left is the example of the Deepwater Horizon oil disaster, which had a huge impact on fishing communities along the Gulf Coast. In the middle is the example of trying to quantify exposures to heavy metals in water and in the fish that live in those water that are used by Native American tribes. And on the right is an example of a smelter site, because of course, many communities are affected by the position of polluting industries. And sometimes that even leads to the need for environmental remediation, for example, Superfund sites. Next slide, please. So when we think about how when exposure assessments are well conducted, they can allow individuals or populations to act against exposures that are associated with an excessive risk. And that data can be used to allow for the promotion of exposure mitigation strategies. Those strategies could be implemented at whole communities or whole populations, or sometimes they can be targeted towards individual people, but they also could be used to put pressure on corporations as a way to move away from the use of a hazardous chemical in consumer products. So let's start to dig into the case studies that we identified and talked about that highlighted some of these problems. So slide number 12, which you've already heard quite a bit about in one of the prior presentations from Dr. Maffini, we know that there's an increasing number of chemicals that are released into the environment. And Dr. Maffini talked about some of the challenges with the fact that those chemicals are evaluated one at a time. But there's also the problem that we can't keep up with the exposure assessments that are needed to account for all of these various chemicals that are on the market. And that even when some problem arises with one of those chemicals, an alternative, regrettable replacement is often introduced. Unfortunately, the identities of many of these chemicals are kept secret and are considered confidential business information. And there's also the challenge of if we don't know what to look for because we don't, for example, have chemical standards, we can't even do the exposure assessments we want to do. Next slide, please. So this is also an example of how exposure assessments can become out of date very quickly. This is an example of glyphosate, a widely used herbicide that's been promoted for use in the use of genetically modified crops. But it's also, the use has changed over time. For example, it's also used as a desiccant, as a way to dry down grains just prior to their harvest. If you looked at exposures and you calculated exposure assessments based on any single year that's shown on this graph, within 5 years, that exposure assessment is already out of date. Within 10 years, it's terribly out of date. Next slide, please. We also noted how exposure assessments can rely on models or assumptions about human behavior that can lead to underestimates of exposure. A great example of this comes from the use of thermal paper, which is often coated with chemicals like BPA, bisphenol A, or other bisphenols that have been used as replacement chemicals. There are a lot of assumptions that have been made about how people hold thermal paper. But in many circumstances, those patterns are actually not true and do not hold for how people use them. And in one study that was conducted in my lab, we showed that 2% of people will do strange things with paper, like putting it in their mouths or using it to blot grease off of pizza. And so we certainly are not accounting for those strange uses when we're doing an exposure assessment that's based on what we might consider to be typical use. Next slide, please. We also talked quite a bit in our paper about how we use models. And in this case, we're talking about PBTK models. So this is physiologically based toxicokinetic models. And in short, those are models that, based on knowledge about the kinetics of a chemical, like how water soluble it is, based on knowledge about how it enters the body, based on knowledge about how it's metabolized in the body, you can make models for how long that chemical is going to reside in the tissues of the body, how long it will take for it to be removed and excreted from the body, and what forms it will undergo that excretion. The problem is that those models are normally based on physiological data that comes from, for example, adult men, which cannot reasonably be applied to the way that children metabolize chemicals or pregnant women metabolize chemicals, as well as the elderly and different phases of our life where we might be at greater risk for harm. So let's move on to some of the recommendations that we made. So let's move to slide 16. First of all, there's actually quite a bit of requirement for the use of exposure data by regulatory agencies to protect the public from toxic chemicals and pollution. And so when we're talking about chemicals that, for example, are considered acknowledged water pollutants, agencies like the EPA must do their job. There's also been a number of international treaties that have been pulled together to restrict or ban the use of particularly hazardous substances. And the U.S. often participates in those conversations. A cynical person might even say that in some ways they reduce the power of those treaties and protocols, but then often they don't ratify them, which means that we might have best intentions, but we aren't required to sort of follow through with them. We also know that one of the best ways for communities to feel powerful and to regain some power is to use corporate reforms and social movements to help encourage companies to reduce exposures to hazards. But of course, this requires that the public knows about those hazards, which means that we need some disclosures. So if we move on to the next slide, that's the second point that we raise here, which is increase the mechanisms to improve disclosures of how chemicals are being used and in what products we can find specific chemicals. We do, of course, need some scientific data, but in the face of that uncertainty, we're not actually calling for more studies. We're calling for the fact that those uncertainties need to be acknowledged in the risk assessment process. We think that exposure assessments should be required to be reconducted when there's evidence that use patterns have changed. And we think that regulatory agencies need to better account for differences in exposure that are based on the fact that different groups and populations have inequalities in exposures, and that they also have inequalities in their ability to respond to those exposures. And some of those inequalities can be due to their exposures also to violence, to problems with urban design, with other issues with the built environment, segregation, racism, lack of exposure or use of green space, poverty, and many other factors. The EPA should fulfill the mandate that was set out by TSCA to identify and protect populations that are considered vulnerable to environmental insults due to these extrinsic factors. And then if we move to the last slide, we think that the way to do this is to include additional adjustment factors that are used during the risk assessment and risk management steps to take into account for the fact that exposures are not simple. We're exposed to complex mixtures. Again, Dr. Maffini talked about that quite a bit. The fact that we have different stages of vulnerability and exposures can differ across those different stages of vulnerability. We also heard a bit about that. And the fact that there are atypical exposure patterns. So the example of 2% of people use thermal paper in a very strange way. If you think about all the different products that you encounter in your everyday life, are you in that 2% for something? And that leads us to the next point, which is that we need to actually protect that 2%, because people use products in what we might consider to be strange ways because it has never occurred to them that those products might be hazardous. The general public has never thought that we would be handing them something hazardous every time they make a purchase at a cash register till. And so the last point, and we spent a lot of time in our group talking about this and thinking about this, is that communities are experts in their own exposures and communities are experts in their own experiences. And we need to seek guidance from those communities and follow the lead of those communities when we're developing new tools to screen and map for exposures, as well as when we're creating environmental education programs, because education only works when the people who it's targeted to are involved in its development. So I'm really happy to close with that thought, and again would like to just thank all of the other authors of our paper, and especially Swati, who is the behind-the-scenes leader and coordinator in so many ways for this project. So I'll turn it back to you, Swati.
Oh, thank you so much, Laura. And yeah, thank you to all of our presenters. So we're going to move into closing. I just wanted to kick it to Tracy really quickly for a wrap up of this entire project before we get into a Q&A. And I'm really excited to get to all of your questions. So Tracy?
Yes, thank you, everyone. And thank you for those terrific presentations and all the collaborators who participated in this process and our steering committee who helped guide this process. I just want to emphasize some of the key points that came up is that we have the science right now that can be used to better protect the public's health from environmental chemical threats. And these were, all the papers describe very specific actions that can be taken. And I also want to note that many of these actions are based on already existing processes, have already been made by authoritative bodies, including the National Academy of Sciences, or have been implemented by state agencies in the US. And I just want to also note that there are many things that can be improved about the hazard and risk assessment process, but one of our goals was to identify the most important ones that would bring the biggest benefit. So we've been very deliberate about the focus in these 4 different areas and in the recommendations in the papers. So I really want to thank everyone for participating, and I'm going to turn it back to Swati to organize the question and answers.
Awesome. Thank you so much, Tracy. So as folks can see on the screen, we put a ton of work into this project. We have all these beautiful infographics that you saw, sprinkled throughout our presentation today. They're on our website at pre.ucsf.edu under strengthening the chemical regulatory process. All of our lead authors developed these really lovely blogs that were released by our communications team over this past month. You can check that out at the link that's on your screen. And then email me if you want us to come speak to your group. We are open to, sharing all of this knowledge, and we're also really open to feedback. So we really look forward to hearing from you. My email is on the screen if that's what you're wanting to do. We're also really excited to announce, and Tracy, I don't know if you want to chime in here, that we are working on a congressional briefing on strengthening the science behind chemical regulations. So stay tuned for that. If you're connected to PRE on any number of our channels, through the Science Action Network, through our general listserv, keep your eye out for that. And then kind of to wrap it up, this entire project was under the umbrella of PRE Science Action Network, which I coordinate. So for folks who don't maybe know or who found us through another avenue, the Science Action Network amplifies our efforts to promote science in decision-making. So it's a collaborative group of around 200 scientists, academics, and clinicians representing 9 countries, 22 states, and 58 universities, as you can see on your screen. And we collaborate on initiatives like this to improve environmental health decision-making. We all use our differing expertise to contribute to public comments to EPA and to other agencies. We participate in webinars just like this to share the latest environmental health research and science policy actions. And of course, you'll get a bi-monthly science policy news digest from me. So you can learn more at the link that's at the bottom for the Science Action Network. And if you're interested in becoming a member of the Science Action Network, please fill out the bit.ly that's on the link. I just want to clarify, because the hyperlink makes it a little obscure, that it's bit.ly/SAN_interest. And then from that, we'll move into the Q&A. I want to say for more information about PRE in general, please feel free to check out our website and follow us on our multiple social media platforms. This talk will be on YouTube later. We also have all of our infographics on our Twitter, as well as our new Instagram. Please follow us on Instagram. And then as well, the link to the blog there and to our Facebook. So Courtney, I think we'll move to you to uplift some of the questions that we have for our authors. And I will remove the share screen, but if there are questions around something that you saw on the slides, I'm happy to put it back up.
Perfect. Thank you, Swati. Yes, we've organized the questions. We have some general ones, so I'll start with those first, and then we have some that are specific for the authors. I'll also say that we're still keeping an eye in the Q&A. So if you have any, as we're starting this process, feel free to keep dropping them in and we'll grab them as we go along. So some of the more general questions, we've had a lot of questions from folks about whether the slide deck will be available, as well as the blogs and other links that have been shared in this presentation.
Yes. So as I said, the slide deck will be available. We will put likely PDF versions of the slide decks up on our site. The blogs have been available. So our communications team has been releasing these really wonderful blogs with all the differing analogies that you saw from our presenters today. And those you can find at preucsf.blog, I believe. But that was also just on the screen, and we'll drop it in the chat.
Perfect. Thank you. And then the other general question we have is whether there's somebody on our team who's specifically looking at pesticides.
Tracy, do you want to take that?
But the recommendations that we have throughout these presentations are equally applicable to whether the chemical is being registered under TSCA or pesticides. We have done some work in the area of pesticides. I think if you have any further questions, you should email Swati and we can see if we can answer your question offline.
Great, that sounds good.
Great. All right, now we have some questions for Dr. Maffini. The first question is, wouldn't a particularly important class to group is all of the persistent chemicals? So for example, PCB or PFAS.
Yes. I want to clarify that Congress actually was the one that had put a ban to PCBs a long time ago. So that is the class that was effectively banned by a congressional decision. On the case of PFAS, yes, I think pretty much everybody's advocating for a class treatment of PFAS. And there are many different ways to look at that particular class. It could be about bioaccumulation in the body, it could be about persistence in the environment, that is pretty much all of them. But depending on which decision you want to make, the groups will look different, perhaps.
Perfect. Then we got one more question for you. They say, thank you for this excellent talk. This work addresses hurdles and questions that I've had for years, and class-based approaches seem critical. Do you see any issues related to non-synthesized or elemental toxins that appear in products through intention or contamination? Yes, I'm thinking about heavy metals versus trace minerals.
I think it does. I mean, the Food and Drug Administration has a program undergoing now called Closer to Zero, where they identify 4 neurotoxicants, arsenic, lead, mercury, and cadmium. And they are going to look at them together as a group for cumulative effects in children's development. So yeah, it would apply to any kind of compounds.
Can I just add something there too? So one of the National Academy of Sciences reports that this is based on is evaluating cumulative exposures to phthalates. And in that report, they recommend, which I think you have, Marisol, on this, is that you evaluate chemicals based on the similar adverse health outcomes. And in that report, they actually make a recommendation that another opportunity, in addition to doing phthalates, is lead, mercury, and PCB, so chemicals that affect neurodevelopment. So yes, definitely.
Thank you. All right, we have some questions for Ms. Nielsen. The first one is, how do these recommendations connect with Dr. Maffini's recommendations to assess and regulate chemical groups? Also, don't regulators currently often waive or reduce the 10 times safety factor? How can we prevent this?
So I think the central question here is really how does it relate to regulating chemicals as a class? And I think if you're setting health-based standards in a large group of chemicals, you're probably regulating based on the chemical with the highest demonstrated toxicity. So the methods would apply, but just be based on perhaps the chemical that's particularly data rich that you can do the modeling for. or something along those lines.
Great. And then another question is, would the probabilistic approach you discussed be able to take into account potential non-monotonic DR effects?
Yeah, so a non-monotonic dose response effect where you maybe see a different relationship between the chemical under question and the health effect, depending on the exposure level. I think you could do a probabilistic risk assessment based on that. You just might be zooming in on specific portions of the dose response curve. So looking at, a linear range for multiple different ranges of the chemical based on the direction of the effect. So it's definitely something to think more about, but these methods likely can have some flexibility in the models.
Wonderful, thank you. All right, we have a couple for Dr. Vandenberg. The first one is, has anyone calculated how many different chemicals a person living in different areas of the US might be exposed to? I'm thinking if a person is exposed to 10,000 different chemicals, who knows how they interact with our bodies?
Oh, wow. That's a great question. I'm not aware that there's really good data in this area. The problem really has been that up until very recently, people have only looked for what they know to look for, right? It's like the terrible Donald Rumsfeld quote of, what about the unknown unknowns? Now that there's more untargeted analysis approaches, I think that we're going to be able to have a better sense for those numbers. But that work still, even the untargeted analysis approach has really been limited not to large populations, but to individual people. So the real question gets at how different are people depending on where they're living or depending on some other factors. And the real answer right now is, I don't think that we know. What we do know from biomonitoring is that features like socioeconomic status, gender, race, and ethnicity absolutely play a part in the levels of exposures to different chemicals.
Thanks, Dr. Vandenberg. All right, we have some questions that I'll pose to all of the lead authors and individuals that worked on this. So the first one is, is there any mechanism currently that ties human exposure data and adverse health outcomes back to the regulators?
Does that mean like regulators get some sort of star rating based on how well their decision is? Is that sort of the interpretation of that question? Because the answer would be no. There's no Yelp review.
Can you repeat that question, actually, Courtney?
Yes, it is. Is there any mechanism currently that ties human exposure data and adverse health outcomes back to the regulators?
Okay. I interpreted that to mean, is there any mechanism for us to share that kind of data with regulators?
Courtney, do we know who asked that question, if they're still on the call?
I'm looking back, I don't know off the
I
top of
asked
my
that
head.
question.
Oh, hi, Richard.
Perfect,
Yeah,
thank you.
perfect. Thank you.
Good. No. Like actually right now, I'm working on developing a national platform in Canada for linking adverse health outcomes to exposure data. We got a lot of support right from across Canada on doing that sort of thing. And then the idea is to give the best science back to the regulators so that they can do informed policy making. Because right now that sort of thing is not happening. But some of the presentations I saw today were perfect present, they're really right up the alley that we're working on. We've been working on this for some years. But the idea is right now, I can tell you in Canada, I don't think that there's any of that kind of evidence that feeds back to the regulators. They look at, what were they presented by the lobbyists and so forth. At least that's my impression. But that's the impression I have is what's going on in the US as well, in a large degree. But it'd be really nice if we can collect as a group of academics and so forth, the exposure data to adverse health outcome, and then feed that back to regulators and say, aha, here's a signal. We need to cut back the limits, whether it be something by glyphosate or some other chemical, whatever, but we need to start cutting down those limits on what's acceptable.
Yeah, I wanted to, thanks for that comment. I don't know exactly how it works in Canada, but in the United States, we have an administrative review process. So that means that every decision that EPA is going to formally make goes through a public comment period. So that's one way that we have been through the Science Action Network and will continue to be, particularly with these papers now, be providing comments to EPA so that they specifically have, and they are required to respond to the comments as part of that. So we'll have an opportunity to feed back into the process. I mean, there's many processes going on. So we're going to be focusing on the Toxic Substances Control Act implementation, but we hope that other people who, like yourselves, can take this and feed it back into other processes that they're involved with similarly.
It's a complex thing, and it requires a lot of analysis of what are people being exposed to, and then what are their health outcomes, and then feeding that back. So a public commentary by an individual can't do this. It has to be done by a network.
Right. Well, that's one of the goals of the Science Action Network that Swati organizes.
I'm in.
Well, I was going to say, this is Julia Varshovsky. I was going to say, maybe this ties back into the question from Robin Dodson of what strategies do we think will get the EPA, along with the FDA and the CPSC, to take up the suggestions and use these updated data, even if we can supply them? Is it legislation that's needed? Is it what you just mentioned, Tracy, with your effort to work on TSCA?
So yes, to answer the question, I think that this part of it is, I think that it's a multi-pronged initiative, right? We work with other scientists, we disseminate these ideas, and as I said, many of these ideas, recommendations have already come from National Academy of Sciences reports. So we've collected them, updated them slightly, showed how they can be applied, and now one step is, as Swati mentioned, is to talk to staffers and Congress about what the implications are so that they can take up these activities. Another is to utilize the process that's been going on around implementation of TSCA, because that's where there are legal requirements to both put out the decisions that EPA is about to make, and we can then submit comments, and EPA is legally required to respond to those comments. And then if it's not an adequate response, there are legal remedies, legal approaches to remedy that situation. So, and then I think the other thing is to continue to disseminate it in scientific venues and teaching and dissemination through educational mechanisms.
Yeah, I just wanted to chime in really quickly also that I of course, everything that Tracy said, right? The plan is to have a clear dissemination strategy. This is part of it. We really hope that all of you will reach out to us and work on coordination. I also just wanted to uplift something that's kind of a larger systemic problem. So that is really fundamentally around resourcing and support, right? So for example, the ATSDR was started years ago when there wasn't actually a capability for EPA to track disease. However, it's never actually been funded nor able to do something that is literally a part of its original mandate, right? Which is to be a disease registry. And so I think that, you know, the amount to which we are also able to collect these recommendations, one of the things that we wanted to make sure to uplift was that our recommendations are things that EPA can incorporate now, right? There are things that we are recommending that are well established in the science. We've referenced that NAS report from 2009 that is, you know, over 10 years ago at this point, right? And so, yeah, I just wanted to uplift that as well, that there is, of course, a resourcing problem, and we were being very mindful about it. Courtney, I think we have one or two more questions, and then.
Yes, we have one more question that I will pose to everybody, all of our lead authors and the pre-leads. Has anyone used geocoding or data such as the EJ and Viro screen to better understand health exposures? If so, have you used the census tract level data to think about harmful exposures and their impact on health?
I think one thing that comes to mind based on, being able to kind of define a relationship between non-cancer health effects and exposure levels is that you could really use geocoding data to think about where the largest burden of disease is if you're able to kind of establish that relationship between the exposure level and severity and magnitude of effect.
Yeah, I'll also just identify something that we uplifted in our fence line assessment comments, which you could find online, and something that we also discussed at length in our conversations in the exposure group, Laura, which is that there are also, of course, limitations when we're thinking about trying to make recommendations that account for risk to those who are most marginalized. A really good example of a limitation of census tract data is it will not account for unhoused populations, right? Census tracts
that's
are
exactly right. Yeah.
like it will not account for unhoused populations. It will not account for like different populations, let's say on tribal lands, depending on how those lands are cut. Laura, I don't know if you have any more specific examples, but I think it's also about accounting for the ways that the systems that we have built fundamentally are not able to see the people that really need to be seen and who are disproportionately burdened by exposures to toxic chemicals.
I think that's right. But I do think that we should encourage more people to use the EJ screen tools, especially as teaching tools, because they're so enlightening for young people to see how zip code influences exposures. That's very important.
Yeah, I agree. And another component of this project as well, wanting to be really expansive across tenure and career and age and everything, is right on that point of wanting to make sure that we use tools like EJ Screen and then also show how they work and show their limitations to some extent to help a newer generation of scientists recognize and improve the ways that we account for human health risk. Anything else, Courtney?
Nope, that is all we have.
Excellent. Tracy, did you want to close?
Yeah, just thank you everyone again, and reiterate that first I want to thank all the presenters, all our collaborators, for participating in the webinar, that we have all this information available plus more, and that these are all very specific recommendations that can be adopted now. And while we're always looking to improve the basis of the science that goes into these decisions, we have plenty of science, and we know where there are inadequacies in our implementation of that. So looking forward to, this is just one part of our further activities on this. As Swati mentioned, we'll be going out and talking more about this, working through specific recommendations, including the congressional work that we're doing, as well as working with the specific regulatory agencies. And thank you so much, everyone.